which is also called a large margin classifier. So it is again a classification algorithm. So we have so this is another supervised learning algorithm. Okay, and the outline of the lecture would be that we will start by revising the logistic regression, because logistic regression is also a classifier, and we will see that how to modify the cost function for this algorithm support vector machine. Okay, and then we will look at the intuition, or the that why will a different cost function give us a large margin classifier. Okay, so this is how we will proceed, starting from the recap of logistic regression. So in logistic regression, my hypothesis is given by this equation, and we use this function, which a nonlinear function called logistic function. Logistic function, or we can call it sigmoid function. And the reason to use this function is because we want to have a hypothesis, or the output of the hypothesis to lie between 0 and 1. Remember, in case of binary classification, there are only two classes, and simply using theta transpose or theta dot x was giving us, any value between minus infinity to plus infinity. But we want to constrain that the output to 0 and 1, because we know that there are only two classes. So we use this sigmoid function, and the sigmoid function, the equation is written here. This is how we have the hypothesis, and this is the score function that we have, theta dot x. If we plot the sigmoid function, the g function, or this logistic function, or in case of logistic regression, we usually denote it by the sigmoid function, this symbol. Then this is the curve that we get. So this, on the x-axis, is the score, theta dot x, and on the y is the output. So it always lies between zk, exactly at x z is equal to 0. The value is 0.5, and for positive values it is greater than 0.5. For negative values, so negative means the negative of, I'm talking about the x-axis. For theta dot x less than 0, I get the value which is less than 0.5, and if it is less than -4, then almost I get 0. Similarly, if it is the theta dot x is greater than 4, then I get almost, the value is 1. And then we also said that we are going to say that this output is basically the probability that y belongs to class 1. Okay, so this has the logistic regression has the interpretation of giving us the probability. Okay. And so what we wanted was that if y is 1, we want that h of x, our hypothesis, is 1, and we obtain that by using this sigmoid function, because we know that if theta dot x is greater than 0, for the value greater than 4, we are getting the value 1. Similarly, if y is 1, we are getting y, if y is 0, then we are getting the hypothesis as 0 for values which are less than, -4. In between, we have this curve, but so whenever the hypothesis is less than 0.5, we say it belongs to 0 class, and if it is greater than 0.5, we say it belongs to the class 1, or class with label 1. So this was logistic regression. Let's look at the cost function of logistic regression. The cost function had two parts corresponding to the case when y is 1 and the case when y is 0. So let's look at the case when y is 1. What we want is that the cost function you should be 0 when our hypothesis is giving us 1. So if we, so this is, this is the cost function for the case when we have uh, when y is 1, and this is the cost function when y is 0. And if we plot this part here, this is the figure that we get, and this is what we want actually, that if theta dot x is greater than 0, the cost function should decrease, and for values greater than 3 it is almost 0. Similarly, for the cost function decrease, and eventually it is also going to go to infinity. Okay. So this is the this is the plot of the cost function, and this is what we want. Okay, theta dot x is greater than 0, then the probability is also greater than 0.5. The cost function decreases for values really big, like greater than 3, we get cost function almost 0. Similarly, for the case when y is 0, we have a curve like that, and when theta dot x is less than 0, the probability or the output of the hypothesis is less than 0.5, and the error decreases, and eventually it goes to 0 when theta dot x is less than -3. And similarly, it is going to increase and go to infinity if theta dot x is greater than 0. Okay? To write the cost function in a single equation, we multiply that by the first part with y, the second part with 1 minus y. The reason is that if y is 1, then this part will go away, because 1 minus 1 is going to be 0, and we will be left with only the positive cost function. And similarly, when y is 0, then we need to have a cost function, then this will go away and this will remain, and we will be using this cost function. Okay, this is just a way of writing the equation, these two equations in a single equation. Okay, so this was the cost function, and now let's try to compute, or let's try to find the cost function for the support vector machine. Okay. So we will modify the cost function for the support vector machine, which is a different classifier that we are studying today. And right now we will just try to obtain a new cost function, and then we will see why this new cost function is helpful, or what are the properties of the new cost function. Okay, so let me write the cost function for the support vector machine. So instead of writing the cost function for the logistic regression, what I'm going to do is to write the cost 1, y1, because this is the part, or this is the cost when y is 1, and basically this depends on x, I, y, I, and my parameter is theta. Similarly, I have the cost function for 0. And as before, we have this, and we'll also multiply with, just to write this in a single equation, we also multiply with y and 1 minus y. Okay, and then we also have this regularized, well, this is the regularized version of the logistic regression, so let's also add that. Okay, in case of support vector machine, instead of the lambda parameter here, we are going to have another parameter c over here, and maybe just, and the reason for adding this C here is, well, we will see that, but its effect is very similar to lambda, because remember, increasing lambda or decreasing lambda is going to make this term go away, and we will be not doing any regularization. Increasing lambda will increase the regularization, and the effect is that if you increase lambda here, then this part has more weightage than this part, so you are doing more regularization. So if you remove lambda and then add a constant c here, then increasing c is going to give more weightage to this, and decreasing c is going to give more weightage to this. Okay, so here increasing c will cause less regularization, and decreasing c is going to increase regularization. And here it was opposite, because lambda is with the other term, but their effect is similar. Similar in the sense that you know here decreasing c is going to cause more regularization. So this will be my cost function. Okay, now let's look at the in detail uh, these two parts. Okay, any question up till now? And again, the idea is again the same, that we will minimize this cost function with respect to theta. Okay, we want such a parameter theta which is going to minimize this cost function. Okay. So the next thing is to actually see what are these two cost functions for the case when y is 1 and for the case when y is 0. Okay. Before, let me go back to this slide here. So this slide shows you the cost function for the two cases, for the case when y is 1 and for the case when y is 0. So let me use this slide to draw the cost function for the support vector machine. So what a support vector machine cost function looks like, it looks like that if theta dot x is greater than 1, then the cost function is, then the cost is 0. Okay. So I'm now drawing the cost function for a support vector machine. And if theta dot x is less than 1, then I will have a, a line like this. Okay. Like that. Okay. So, intuitively, it is similar to logistic regression, because the logistic regression shape is decreasing, and once you go past 0 on this side, then a is almost 0. But not exactly like logistic regression. And we will see exactly what are the benefits or what are the characteristics of this cost function. Okay, for now, just we are just going to use this cost function and write the equation for this and come up with a cost function, and then we will see what are the benefits, the characteristics of using such a cost function. Okay, let's look at now. Let's actually now have the equation for this for the red line. It is 0. The cost is 0 when theta dot x is greater than or equal to 1, right? Because it is 0 when it is theta dot x is greater than 1. For values less than 1, the equation is simply 1 minus theta dot x. Okay, so let's actually do that for some of the points. Let's say your theta dot x is, and the output, the cost is basically 1. So by putting 0 here, you get 1, right? Similarly, when the output, the cost 2, so 1 minus theta dot x is minus 1, you get 2, and so on. So this is the equation for the curve जो मैंने यहाँ बनाया, and this is the cost when y is 1. Now let's look at the case when y is 0, how will the cost function change? It will have a curve like this, and at 1 the cost should be 2, at 3 4, and then this line. Okay. And similar to the case over here, let's also write, so this was for this one. Now for this case we have the cost here written. The cost is 0 if theta dot x is less than or equal to -1, and it is 1 plus theta dot x if theta dot x is greater than 1. ठीक है, तो इस केस में देखें यहाँ 1 माइनस थीटा डॉट एक्स है, यहाँ पे इसके इस for y is equal to 0 you have 1 plus theta dot x. Okay, so this is the cost function we are going to use. So again, this is the cost function when y is 1, and what we want is that theta dot x greater than 1 should be, the cost should be 0, and for y is equal to 0 we want that theta dot x less than -1, the cost is 0. Look, so what we want is although when theta dot x is equal to 0, if you remember the logistic regression, the output was 0.5, that middle. But in case of support vector machine, what we want is that not only your theta dot x should be greater than 0, but we want k should be greater than 1 for the case when y is 1. Okay, we are not saying we have a cost function like this. This is also a reasonable cost function. Whenever theta dot x, sorry, for the positive case, let's be talking about the positive case, that this is also a reasonable cost function. Whenever theta dot x is greater than 0, we have 0 cost, and whenever it is less than 0, then we have the value itself. The theta dot x is the cost. But what we want is theta dot x should be greater than 0, only then we are saying कि हमारी cost जो है 0 होगी. ठीक है? So we are pushing the positive boundary even further. Similarly, in this case, we are pushing the negative boundary even, ताकि there should be some gap, which we will discuss in the coming slides. ठीक है? Okay. So so actually let's also write. देखिए यहाँ तो मैंने लिखा था in terms of in this form, but we can also write it in a single equation. Is that 0 and 1 minus theta dot x, right? क्योंकि whenever whenever you are on 1, so if this is greater than 1 or exactly at 1, you're going to get 0. Okay, क्योंकि theta dot x exactly at 1, the cost is 0. Sorry, what I'm doing. So exactly at theta dot x, you get 1. So 1 minus between 0 and 0, so you get the cost is 0. For positive values, for values greater than 1, the cost would behave like this. आपके पास, you are going to take the max between 0, 1 minus, so theta dot x, let's say it is 2, 1 minus 2, so you're going to get 0 minus 1, and so max of 0 minus 1 would be 0. So for all values greater than 1, you're getting 0, which is what we want. And for all values less than -1, this value will be negative. For example, starting from the case when theta dot x is, let's say, 0. I'm talking about the case here. When theta dot x is 0, then max of 0 1 is 1. So I am getting the error is 1, which is what I am getting. Okay, so this is how we are going to write it in the equation form. Similarly, here also we can write it as this 0 1 plus theta dot x. Okay, so in the next slide we have exactly that. Okay, so this is for the case, for this case, and this is for the case. Okay, और यहाँ 1 माइनस है, यहाँ आपका well actually it is 1 plus theta dot x. Okay, now the thing is instead of having two different equations for y1 and y0, look, for y0 we have the equation is 0 1 plus theta x. ठीक है, यहाँ माइनस है, यहाँ प्लस है, तो इंस्टेड ऑफ हैविंग दीज टू डिफरेंट इक्वेशंस वी वांट के हमारे पास एक इक्वेशन. How can we do that? What we can do is to using a single equation. तो उसके लिए what we can do is we can our core function with y. Now when y is 1, then this will become, when y is 0, then if we put it 0, then this whole term goes away. So this is not right. So what we are going to do instead is to change the variable. Instead of using y is equal to 0, we are going to say okay, the two classes have labels 1 and -1. Okay, because these are labels, we does not matter if the label is 0 or -1 or the label is a or b. So whatever makes things easier for us, we can use that as our label. So instead of using 1 and 0, we are going to use the labels as 1 and -1. Now if I have y and I change it -1, then it becomes 1 plus theta dot x. Okay, so that is why what we are going to do is basically, okay, instead of using 1, we are going to use the label -y, and then these two equations, they are exactly same. Okay, so now the cost function is basically this term or the other term, they are equivalent. So the total, the overall cost function is written here. Okay, let me again write it just to so you better understand. Okay, this is the cost y I theta x I. Okay, and of course we have to take the sum over all values of the data points. So I goes from 1 to n, and we also have this part here, and then we have this constant, the parameter, the trade-off parameter c. Now this is the cost function, and I have to minimize that this cost function. Okay, there is one more change also, that the hypothesis function is basically what we want is whenever theta dot x is greater than 1, we are assigning it +1 class. Whenever theta dot x is less than 1, less than -1, we are assigning it a negative class. So we use this function sign, which is simply going to read off the sign and assign that value to the to the input x. So for example, if theta dot x is +5, then this function sign is simply going to read, it's going to output +1. It belongs to class +1. Similarly, for a point, data point x, I get theta dot x -4, let's say, then it is going to read out the sign and give me that it belongs to class -1. So this, for SVM, this is the hypothesis, and this is my cost function that I have to minimize. Okay, any question? Okay, so let's
सर
move
साइन
forward.
साइन फंक्शन की वैल्यू क्या होगी अगर वैल्यू 1 और -1 के दरमियान हो?
साइन फंक्शन की वैल्यू मतलब whenever it is greater than 0 it is going to give us +1, whenever it is less than -1 it is going to give us -1, and in the values between at 0 or between 1 and -1 basically it is you don't have a decision, it is not determined. ठीक है, तो उसमें आप कुछ उसके बारे में कुछ नहीं कह सकते. Okay. तो यहाँ तक तो हम तब देख चुके हैं, वी नो कि हाइपोथेसिस क्या है एसवीएम के केस में, एंड व्हाट इज द कॉस्ट फंक्शन, एंड वी इन डिटेल के किस तरीके से कॉस्ट फंक्शन हमने डेवलप किया है. बट नाउ लेट्स लुक एट द रीज़न के व्हाई आर वी यूजिंग दिस एज कॉस्ट फंक्शन, एंड यू नो इस पूरे का क्या रीज़न है, क्यों हमने चेंज किया. लॉजिस्टिक रिग्रेशन आपके पास का कॉस्ट फंक्शन जो ब्लू में है, इसकी बजाय हमने ये रेड में ड्रॉ किया है, इसको यूज़ किया है. तो व्हाट आर द बेनिफिट्स और व्हाट आर द कैरेक्टरिस्टिक्स और व्हाट काइंड ऑफ ए बाउंड्री decision boundary this SVM support vector machine is going to give us. ठीक है, so let's now discuss that. Okay, so let's look at this example कि आपके पास दो classes हैं in blue and in red. One of them is +1 class, the other one is -1 class, and so you want to have a decision boundary between these two classes. So obviously ये तो it's not right, it is giving you errors. So but this one is also okay, at least on the training example it is not giving you any error. This is also okay, and this one is also okay. But which one of these three classifiers is a better classifier? Obviously you would say intuitively that this looks like better, and the reason is that even if you rotate it or change it a little bit, it's not going to start making misclassifications. However, in this case and in this case, if you change it slightly, or you rotate it, you move it, translate it, you may start getting errors. ठीक है, तो इसलिए you want a classifier, a decision boundary जो कि which should be in such a position के that even if you move it a little bit, you have some margin of error. Okay, so with that, let's look at this definition. Okay, define the margin of a linear classifier as the width that the boundary could be increased by before hitting a data point. ठीक है, तो what this says is कि अब यहाँ से इसकी boundary जो है, so this is the decision boundary, right? Now let's move it or draw parallel lines on both sides of it. अब इसके हम पैरेलल लाइन ड्रॉ करते हैं, लेट्स से इस जगह पे एंड इस जगह पे. So these are parallel lines which are drawn equidistant from the decision boundary, and if we increase this width or this margin, then we start to touch the data points. Okay, so this defines the margin कि कितना आप ये line draw कर सकते हैं कि before you start touching or hitting the data points. Over here also, if I try to do the same on this figure, so I don't have a lot of margin. Okay, so I can only draw like this. Okay, these are the the lines uh, or the margin before I start hitting some data points. Similarly, over here also, it's very close to the data point, so I don't have a lot of margin. Okay, so what is margin? It is, you can say, the width, this width here, or this width here. ठीक है. And what we want is कि जो भी classifier या decision boundary हमारे पास हो उस it has the maximum margin possible. तो इसलिए इसका मार्जिन भी कम है, इसका मार्जिन भी कम है, इसका मार्जिन आपको इस केस में द बेस्ट पॉसिबल लग रहा है. ठीक है. Similarly, let's say instead of that, let's have another decision boundary over here. So for this case, since we have it is not in the middle of the two classes, the decision, the margin would be something. Let me draw with a different color. Red line is the now the decision boundary, and margin I'm drawing it with blue. So something like this. Okay. So this is the width, because if I move it any further, I'm going to start touching these red points. So given the definition of the margin and our objective, this seems like the best approach. It is giving us a line which is which has the maximum margin possible. Now we will see that how by modifying or by using the cost function that we have for SVM, we are actually getting this kind of a classifier. Okay? The cost function that we have studied for SVM, it actually gives us this kind of a classifier. So we will actually now see why does it give us a classifier like that. Okay, ये बात हम डिस्कस कर चुके हैं कि intuitively this feels safe if we have made small error in the location of the boundary. Which means that if we change it, rotate it, this gives us least chance of causing a misclassification. And another definition is of support vectors. Support vectors are those data points that the margin pushes up against. So for this case, the support vectors are, this data point and this data point, because these are the data points that lie on the two planes that I drew in the before. Okay, basically, these two lines they lie on these data points. So those data points that lie on those boundaries, they are called the support vectors. And the idea is that why do we call them support vectors? Because for this example, for example, if you remove this point or if you remove this point, the decision boundary will not change, because the decision boundary only depends on the closest 2 points. If you change them, if you remove them, then of course your decision boundary will change. But other than that, all these points, even if you move them, if you add another point here, it will not make much of a difference on the decision boundary itself. Of course, if you add another point here, blue point here, or a red point here, then the decision boundary will change. But if your data points, they are not one of the support vectors, then the decision boundary will not be affected by them. Okay? And this makes your SVM classifier very robust. By adding or deleting some points, your decision boundary will not be affected unless and until those points are your support vectors. Okay? Okay, so I think instead of taking the break in the middle, we finish the lecture and then we will take a break a little earlier. Okay? And by the way, आज मैंने क्विज भी आपका रखा था, लेकिन I forgot कि आपका खासतौर पर जो सेक्शन ए को क्लास थी वो मैंने थोड़ी सी लेट ली, तो पिछले टाइम के मुताबिक रमज़ान का मुझे याद नहीं रहा था, तो आज क्विज होना था आपका, लेकिन फिर आई हैड टू चेंज द क्विज टू टुमारो. तो कल आपका क्विज है, और the quiz topic is from artificial neural network. It will be the MCQ quiz on LMS, and we will have about 15 minutes for that. Okay, so let's continue with the lecture. So when we studied the logistic regression, if you remember, we looked at the interpretation or the geometric interpretation of the decision boundary, that how does it divide the positive of one class from the other class. So let me briefly go through that. When we look at this function dot theta dot x, what we are basically doing is, in 2D as, as it is shown here, this you can also write it as theta and cos d, where d is the angle between these two vectors. Okay, and whenever the angle is acute, cos theta would be positive. So this is also positive because it's a magnitude. This is also positive, which is magnitude. So your theta dot x will always be positive whenever you have a data point which is making an acute angle with your parameter theta, which basically means that anything that lies towards this side, and all those points that lie exactly at 90-degree angle, which is this line here, all points that lie on this, they make 90-degree angle with theta. This is your parameter that you have found. Then your then you are going to get theta dot x would be exactly 0, because theta cos 90 is 0. So your theta dot x would be 0. So this line is the decision boundary. On one side you have one class, on the other side you have other class. All points that lie on this side, they will make obtuse angle, and hence theta dot x would be less than 0, it will be negative. This okay, so let's look um at the distance of a point from the decision boundary. Okay, let's say any point, you are given a point here, then what is the distance of this point from the decision boundary? And it is drawn there. Let me actually draw it again here. So let's say you have a point which is this x, okay, and you want to find the distance of this point from the decision boundary. So this is your point, this is your vector for the point x. Now when you take the dot product between theta and x dot x, then what you're doing is, or what is basically, what is the projection of x on this theta? This is the projection basically. If I'm talking about this line here, this is the projection of x on theta, on the vector theta, and you can write it like this: x cos theta, right? So this is the projection of x on theta, and this projection also gives you this distance, basically the distance from the decision boundary. Okay, so you can use basically theta dot x to compute the distance from the decision boundary, because theta dot x is, this part is the, and then you need to divide by theta just to get only your distance. So you can use the theta dot x to compute the distance of the point from the decision boundary. And distance from decision boundary of a point x is basically, as I wrote before, theta dot x divided by the norm of theta. ठीक है, just let me मैंने delete इसको कर दिया है. Anyway, this basically, this is the distance. So when you so theta dot x is basically giving you theta x cos d by d is the angle between theta and x. But the distance, for the distance you have to actually divide by the magnitude of theta. Okay, so this is basically the distance of a point from the decision boundary. But for a point on this side, your theta dot x is negative, right? ये हमने यहाँ discuss किया था कि because it is making obtuse angle, so theta dot x is less than 0. So what you need to do is to multiply this by, for a point which lies on the other side, you need to have minus to get the actual distance, because minus 4 is not a distance, 4 is a distance. So in order to get just the distance, you need to multiply with minus. So this is what I have here. Okay, for if theta dot x is greater than 0, which basically means all points that lie on this side, the distance is given by theta dot x divided by the magnitude of your parameter. And similarly, for points that lie on this side, theta dot x is less than 0, so you have minus theta dot x divided by the magnitude of the vector. As before, we want to write it in a single equation, so we multiply by y. Okay, because y for all points that lie on this side is +1, for all points that lie on this one is -1, so you are basically multiplying by -1 automatically when points lie on this side of the decision boundary. So this is the the distance of a point from the decision boundary. And remember, in the previous slide we talked about the margin, which is this width here. Okay, this width, this is also a distance of this point of the support vector, or any point. I mean, the margin is basically the distance of the support vector from this line, from the decision boundary. Similarly, you can also compute distance of any point from the decision boundary. So let's write the equation for margin. So margin is basically equal to y theta dot x. So in case of margin, we do not actually divide by this magnitude, because margin is basically is proportional to that. So margin is basically the distance. So this is my margin, okay, where so this gives me a sense whether the what is the distance, or if this margin gives me a value which is proportional to the distance of a point from the decision boundary. Now the question is, uh, if I wrongly classify a point, for example, a point lies here and the ground truth label is 1, okay? So what will my margin be? Will it be positive or will it be negative? G. Anyone?
Sir, negative.
ठीक है. Uh, why will it be negative? देखें, क्योंकि theta dot x would be negative, क्योंकि आपका ये point जो है it lies on this side, तो we know कि theta dot x would be negative as theta and x are making obtuse angle. So this will be negative value, and but y is positive, and so in the end I'm going to get a negative value. So margin also tells me कि मेरा जो point है वो सही मैंने classify किया या नहीं किया. Okay, so a negative value basically means that I have wrongly classified on that example. A positive value means I have rightly classified, and the value of this margin, the magnitude of this margin, is going to give me a measure of how how further it is from the decision boundary. It is not the exact distance, because the exact distance में आप ये divide भी करते हैं इससे, but that is also so. But margin is going to give you a value. The magnitude of the margin is going to tell you कि आपका जो distance है वो कितना है. I mean, not distance again, distance आप में divide कर रहे हैं, but you're not dividing that. but it's in short, it is going to give you a value which is proportional to a distance. So this is your margin. Margin gives the distance of a point from the decision boundary. The binary classifier makes an error when margin is less than 0, because if we have discussed this case के आपका point यहाँ lie करता है और उसका ground truth 1 है. Let's also consider the other case कि आपका point जो है वो lie करता है on this side, ठीक है, लेकिन उसका ground truth value -1 है. तो your theta dot x would be positive क्योंकि you lie on this side, but y would negative, so your margin would in the end be negative. So margin is when it is less than 0, you know कि आपका जो binary classifier it is making an error. And margin also gives a measure of confidence. And why is that? क्योंकि my margin जो है it gives you a value. If the value is less, it means your point lies close to the boundary. If the value is greater, is the big value, then you know it lies far from the decision boundary. एक point यहाँ lie करता है और एक point यहाँ lie करता है. This would have a smaller margin, this would have a larger margin क्योंकि उसका distance ज़्यादा है. तो अगर आपने सही classify किया, then you are more sure about this point क्योंकि it lies very far from the decision boundary. You are 100% sure कि ये तो एक ही ये जो negative class ही है. Similarly, on this side also, if it lies really far from the decision boundary, you are 100% sure कि it is a positive class. For points which lie close to the boundary, you maybe you are right, maybe you are wrong क्योंकि a little bit movement of the decision boundary can make that point positive or negative. So the magnitude of the margin tells you how confident you are in your classification. और इसी तरह अगर आपने wrongly classify किया और उस केस में भी आपका margin आपको ये बताएगा कि how wrong have you, how wrong are you, ठीक है, क्योंकि अगर आपका एक point है जो कि आपने wrongly classify किया है and it lies very close to the boundary, then you have made a wrong classification, but it is very close to the boundary, so this error is not very big. However, if a point lies here and this is also wrongly classified, then your decision boundary is really off, right? So this margin tells you this confidence measure के अगर आपने सही classify किया है तो तब how confident you are. Similarly, अगर आपने इसको point को गलत classify किया है, in that case also it gives you a measure of confidence. Okay. Okay, any question up till now? Let's move forward and see that what this margin is for the case of support vectors. So this is my decision boundary, this green line here, and let's say कि ये आपके पास एक positive point है x plus, and this is the closest positive point to the decision boundary. If this is the closest, then what we are saying is that theta dot x is basically 1. This is the constraint for all positive points. Okay, for all positive points, theta dot x is greater than 1. Remember that our cost function is something like that. It is not this कि अगर 0 से distance ज़्यादा है तो we are saying कि वो सही classify. We are not saying that. We are saying कि the positive point should be even further from this yellow line. Although कि अगर वो इस line पे भी lie करते हैं green और yellow के दरमियान, still I am getting the value of theta dot x is positive, but according to my cost function there will be some error. ठीक है, देखिए अगर ये इसके दरमियान lie करता है तो I have some error. So what I want is कि my decision boundary be such कि all positive points should be further away from this yellow line कि वो इस तरफ हो, and there should be no positive point even between the green and the yellow line. ठीक है, so this is what I am saying by using this cost function. And exactly at the yellow line, the cost function is the theta dot x is 1, right? This is on the x-axis, theta dot x is 1, and the cost function is exactly 0 at that. So here at yellow line, the cost is 0, but if a point lies here, then the cost, there is some cost. Although वो decision boundary के right side पे है, but still I am incurring some cost. ठीक है? So by using this as cost function, I'm encouraging my decision boundary to be in such a position कि आपका जो जो येलो लाइन है, जो जो आपकी जो मार्जिन है फॉर द सपोर्ट वेक्टर, that should be uh, that should be basically at a place where your theta dot x is +1. Okay. Similarly, for the negative support vector, I want the same. Okay, I want to have the decision boundary in such a position कि all negative point they lie on this side of the yellow line. हम अब green line की बात नहीं कर रहे, yellow की बात कर रहे हैं, ठीक है? क्योंकि if they lie in between, there will be some error, जो कि this much error will be there. So what I want is कि all the positive point they should be away from this yellow line or on the yellow line, and all the positive points away on this side or on the yellow line. ठीक है, exactly अगर जो point होगा इन yellow lines पे उनको हम कहेंगे support vectors, और उन पे अगर वो negative plane पे हैं, the value of theta dot x will be -1, and अगर वो positive plane पे हैं तो theta dot x would be +1. Okay, now what I want is कि जो आपका ये distance है between these two planes, the distance between these two planes, let's actually first compute that. Okay, what is the distance between these two planes, between the these two yellow lines? Simply we have to compute the distance theta dot x minus theta dot x plus. ठीक है, क्योंकि the distance of this point is basically this is distance. Similarly, this distance is given by this value here, or I've said the opposite. Let me say that again. ये जो आपका distance है, this is given by this equation, this distance is given by this equation. मैंने इन दोनों distance को subtract किया है, and this is the value I get, 2 divided by theta, the magnitude of theta. So in support vector machine, what I want to maximize this distance. ये आपका DI should be maximum. ठीक है, this is what we want कि your decision boundary should lie in a way कि आपका जो distance है, this D is maximum. So, or in other words, I want to minimize theta. ठीक है, क्योंकि if you want to maximize to let me use red marker. So the distance between the two yellow lines is this, and I want to maximize the distance. I want to maximize this, or in other words, because what we have been doing is minimize. तो अगर 2 divided by theta को maximize करना है तो सिर्फ अगर आपका इसको यूं कर दें, इसका रेसिप्रोकल ले लें, तो we want to minimize that. ठीक है, so this is what we are doing in the cost function of support vector machine. Okay, we want a classifier that maximizes the distance between support vectors or minimizes, the theta norm of theta, subject to the constraint that my points they are either on this side or on that side. ठीक है, और इस सब को अगर आप cost form में लिखेंगे तो this is the cost form that I get. ये आपका पार्ट आ गया यहाँ से कि this is what I want to minimize, और ये पार्ट आपका ये जो constraints है उसकी वजह से यहाँ आ गया. ठीक है, और यही हमने cost function पहले derive की थी. So this is the cost function which is giving us this maximum margin, and so therefore support vector machines are also called the large margin classifier. और यहाँ जो हमने पहले भी डिस्कस किया था, this C is a trade-off parameter which balances or gives different weightage to this term, and as a result the cost function would either this term would have more weight or this term would have more weight. So we want to find a balance. This is a hyperparameter that you train while tune while training. And if C has a small value, then this part, which is the data term, has less uh, weight or less significance in the cost function. This part would have more significance. So this part is basically giving us the maximum margin. It is basically trying to maximize the margin. So when C is less, you will get a decision boundary which has a maximum margin. And when C is has higher value, has bigger value, then this part has more weightage, more weight in the cost function. So you will get a decision boundary, or you will get a decision boundary in which this will have less effect. So you may not get a decision boundary जिसमें आपका मार्जिन ज़्यादा है, उसकी जो width है ज़्यादा है. Let me give you an example. These are two classes and these are two decision boundaries. एक आपके पास ये वाली है, let me call it 1, the other one is 2. Now which one of these two do you think corresponds to a small value of C? Remember, if you have a small value of C, then this part, which is basically trying to maximize the margin, has more weightage, so you will get a decision bound जिसमें margin ज़्यादा है. So if C is less, so which of these two decision boundaries correspond to a small value of C?
Two.
I'm talking about small value of C. Margin, चल ये पहले बताएं, margin 1 जो decision boundary है उसका ज़्यादा है या 2 का margin ज़्यादा है? So
1%.
remember के देखें, रिमेंबर कि वी ऑल्सो हैव टू सी के इट्स नॉट नेसेसरी कि हमने राइटली क्लासीफाई करना है. देयर मे बी सम मिस क्लासिफिकेशन. हाउएवर, because we have these two terms, this term is trying to make is a data term, so it will try to make your कि आपका जो क्लासिफिकेशन मिस क्लासिफिकेशन है वो कम से कम हो. This is trying to give you a bigger margin, and so this has a bigger margin if you look at these two cases. और ये line है इसका margin कम है, so this line corresponds to a small value of C, and this line corresponds to a larger value of C. And so it behaves similar to the lambda parameter in the regularized logistic regression, or it's not similarly, I mean to say is it behaves the opposite. If in case of the logistic regression, large value of lambda resulted in more smoothing, and less value of lambda resulted in less smoothing or less regularization. Here, large value of C will result in lower bias and high variance, and small value of C will result in higher bias and low variance. It is the opposite of what happened in the case of logistic regression when with the parameter lambda. And this is understandable because in case of logistic regression, the lambda parameter is with this term here. So naturally, by increasing lambda, you are doing more regularization, and more regularization basically means uh, uh, higher bias and low variance. Or it may result in high bias and low variance. Okay, any question? Just to recap, what we did is we looked at support vector machine. Support vector machine is a classifier, and we started off by looking at logistic regression, and then we looked at the cost function of the support vector machine, which is shown here for both the two classes. And once we defined the cost function, then we started looking at the reasons or the characteristics of the cost function. And basically what we found is that this cost function gives us a classifier with the maximum margin, and that is why SVM is also called a large margin classifier. And this is practically a good algorithm and very robust to noise in your training examples. and was and maybe if you go back, was the state-of-the-art algorithm before when before this deep neural networks. And nowadays also on small data sets, it performs really well, and it's used these days as well. Okay. Any other question before we finish the lecture? Okay, thank you. So we meet tomorrow. We are going to again revise the support vector machine, and cover some similar topics, and then we will have a quiz also. Okay, so please prepare the quiz. It will be MCQs from artificial neural network. Okay, Allah Hafiz.
Allah Hafiz.